Okay, so next speaker we have is Qiang Guang from the ANU, and he will speak on existence of convex hypersurfaces with prescribed centro-affine curvature. Okay, take it away.
Okay, so yeah, first, thanks for the invitation. So it's a great pleasure to give a talk in this seminar. So I'll talk about our recent work on the existence of convex hypersurfaces with prescribed centro-affine curvature. So this is joint work with Qi Li from Zhejiang University and Xu Jiawang from ANU. So first, I'll introduce the main object that we study, which is functional for convex bodies. And so we're interested in finding the critical points of this functional. Next, I'll explain why we study this functional and its critical points. And so that is our motivations. So our main theorem is about the existence of origin symmetric solutions to the critical points of this functional. So this is our main theorem. To prove this theorem, we basically need to use the flow method, Gauss curvature flow, and we also need to use some min-max ideas. And in particular, we need to use a topological argument in one key step. Okay, so first let's recall some very basic facts about convex hypersurfaces. So suppose we have suppose M is a smooth closed convex hypersurface in Rn+1, so enclosing the origin, and then M will bound the convex body omega. So that is M is just the boundary of omega. And then if M is a convex, then we know that the Gauss map, which is the outward unit normal nu. So nu is like diffeomorphism from M to the sphere Sn. So for any convex hypersurface, so there are like two very important quantities. The first one is the radial function R, and the second one is the support function U, and they are all functions from Sn to R. So you can see the geometric meaning of the radial function, and also the support function. So these are the geometric meaning. Here is our origin. So this is like tangent plane. So the support function tells us much information about the convex hypersurface. In particular, the eigenvalues of this matrix are the principal radii of M. So this matrix is given by hash of U plus U times the identity matrix. Here, hash is with respect to the unit sphere, and the principal radii is just 1 over the principal curvature Ki. So from this fact, we know that the Gauss curvature, which is a product of all the principal curvature, is given by so 1 over Gauss curvature is equal to the determinant of this matrix. So this one is this equation is a Monge-Ampere equation. So for any convex body in the Euclidean space, and we can always define a polar dual of omega, which we use omega star. So omega star is a dual convex body of omega. So it's just given by a collection of points y such that y dot z less than or equal to 1 for any z in omega. So this is the dual body. Because it is like polar dual, so it satisfies some nice dualities. So for example, the radial function R star is equal to 1 over U. So U is a support function of omega, and the support function U star is equal to 1 over R. So R is the radial function of omega. So they satisfy some nice dualities. So we use K sub O to denote the set of convex bodies in Rn+1 enclosing the origin, and the K sub E to denote the set of all origin symmetric convex bodies. And here origin symmetric just means that omega is equal to minus omega. Okay, so with this definition, we can introduce our main object, which is a functional for convex bodies. Let omega be a convex body in Rn+1 enclosing the origin. and then given two positive functions f and g in Rn plus 1, and then we can define the following functional j of omega. So this one is equal to sum of two integrals. The first one is integration of f over omega. The second one is the integration of g over its polar due omega star. So this functional, so it is just it is just a sum of weighted volumes of omega and omega star. So it is a very basic functional. So we are interested in finding the critical points of this functional. So you can verify that a smooth convex body omega is a critical point of this functional, and if and only if the convex hypersurface bounding this omega satisfy the following PDE. So here U is a support function of M. So the left hand side is just 1 over Gauss curvature. The right hand side is the function G and support function and the function F. So here the X over Ux. So this one has its meaning. So this one actually is X over U of X, but the duality, this is the point on the dual hypersurface atom star, and the grad U plus Ux times X. So the meaning of this term is a point on our hypersurface M. So they have their geometric meaning. So of course this one is the Monge-Ampere type equation. So this is our main PDE. So we are interested in finding solutions to this PDE. So why we started this problem or this function, there are a couple of reasons. So basically, we have 3 motivations. The first one is this functional is related to the Minkowski problem in the sphere. So next, let me explain this. So first, let's recall the classical Minkowski problem. This one is a very old problem. Just asked by Minkowski in more than 100 years ago. So basically, this function in this problem is asking for a closed convex hypersurface in Rn plus 1 such that its Gauss curvature is prescribed as the function f. This problem is equivalent to solve a Monge-Ampere equation. So now we know that as long as the function f satisfies this sufficient and necessary condition, and then we can always find such a convex hypersurface. In this problem is solved by many people like Minkowski, Nirenberger, and Zheng Yao and Pavlov. So the classical Minkowski problem is prescribing Gauss curvature in the Euclidean space. Then a natural question is to consider the corresponding problem when the ambient space is the sphere Sm plus 1. So this is the so-called Minkowski problem in the sphere. So the problem is asking for a closed convex hypersurface in the sphere Sm plus 1 such that its Gauss curvature is prescribed as a function f. So for convex hypersurface in the sphere, then it must be containing an open hemisphere, and it will bound a convex body in the sphere. So for a convex body in the sphere, just as the case in the Euclidean space, and we can also define its polar due. So its polar due omega star, of course, it is also a convex body in the sphere. So it is given by the only difference compared to the Euclidean case is here the dot product becomes x times 1 less than equal to x dot 1 y less than equal to 0. And then the boundary, we use M star to denote the boundary of omega star, which is another convex hypersurface in the sphere. So actually, this M star is just a Gauss map of M. It's just a collection of unit normal of M. As in the case in Rn+1, we also have some nice duality. With Gaussian curvature, K is equal to F, and then for the polar dual or the dual hypersurface, its Gaussian curvature K star is equal to 1/F. So it turns out that we can just formulate this, formulate the Minkowski problem in the sphere as the variational problem. So we can consider the following functional for convex bodies in the sphere. So let omega be a convex body in the sphere, and we consider the functional G of omega is equal to, this is just the volume of omega, and the second term is 1/F over its polar d omega star. And you can see this functional is very similar to our functional. The only difference is here, where here the ambient space is a unit sphere. So you can verify a critical point to this functional will give us a solution to the Minkowski problem. So last year, also together with Qiang and Qiang Guang, and we show that, okay, this Minkowski problem, so this problem admits two smooth solutions for any function f. So we also use the flow method and some min-max arguments to prove the existence of this problem. Okay, I'll skip this 3 remarks. So okay, after studying this problem, we thought, okay, why not study the case when the ambient space is a Euclidean space? So then we just investigate this elegant functional when the ambient space is Rn+1. So that's this is our first motivation. The second motivation is actually a special case of our main PDE is corresponding to the prescribed centro-affine curvature problem. So that is when f is equal to 1, and our main equation becomes a following PDE. And this PDE will give us a solution to the prescribed centro-affine curvature problem. So this problem is just given a given function g, and we need to find a closed convex hypersurface in Rn+1 enclosing our region such that its centro-affine curvature at point P is just equal to the function, is just equal to g of P. So what is a centro-affine curvature? So the centro-affine curvature of a hypersurface M at any point P is just equal to the Gauss curvature Kp over d to n+2. So this d is the distance between the origin and the tangent plane of M at point P. So in other words, actually dp is just equal to the spot function u of nu p. So we can just write Kp, we can just write the centro-affine curvature as 1 over determinant of this matrix times u to the n+2. So if you move this term u to n+2 to the left-hand side, and the left-hand side is just 1 over the centro-affine curvature. So the centro-affine curvature, it is invariant under like special linear group, and it just because this invariance, it appears in some affine geometry, and also in maybe in some applications in like image processing. So for this function, Qiang Guang and they prove the existence of solutions when the function g just converges to a constant at a certain rate. So their solution is up to a Lagrange multiplier. So here is a lambda. So lambda is a Lagrange multiplier. So when we study this equation or the centro-affine curvature problem, one main difficulty is that for this function there is no a priori estimate for solutions, for general functions. The simple case is okay if you just consider g is identically equal to 1, then actually any ellipsoid with a unit ball volume has constant centro-affine curvature 1. So they all have centro-affine curvature 1, but the shape of this ellipsoid can be very bad. So this means that in general there is no a priori estimate for solutions. I'll skip that. Okay, this is our second motivation. The third one is that, okay, our PDE is related to the so-called LP due Minkowski problem. So roughly speaking, this problem is just looking for the solution to this Monge-Ampere equation. So the LP due Minkowski problem unifies the classical Minkowski problem and the LP Minkowski problem, and also the due Minkowski problem, and many other geometric problem. And there are extensive works on this problem during the past 30 decades. Due to the time limitation, I'll just I'll skip this. So our PDE and our equation, this LP and Minkowski problem, they have some overlapping cases, but they do not cover each other. Okay, so this is our third motivation. Okay, let's come back to our functional and the main PDE. Okay, so our functional J omega and the Euler-Lagrange equation of J, which is equation of the critical point, is the following equation. So the determinant is equal to G over this one. So we also call this one this problem the prescribed centro-affine curvature problem, just because if we move the term u to n plus 2 to the left-hand side, then the left-hand side becomes 1 over the centro-affine curvature, and the right-hand side is given by function g over f. So this is also prescribed centro-affine curvature problem. So here f and g, they can be any functions. So in order to find the solutions to this equation, and we consider the following condition. So we assume the following condition on f and g. We assume f and g, they are even functions, and also f is bounded from below. So g goes to infinity, g of z goes to infinity, and when z goes to infinity. So why we assume this condition? So one purpose is that, okay, we want to relate the functional j, the value of the functional j, with the information of our convex body. So that means we want to once we know the value of the functional j, and we want to know what is the shape of our convex body, and what is the volume of our convex body. So that's why we assume this condition. So this function, so this condition is not that strong. It still includes a large class of functions. Okay, so under this condition, so our main theorem is that, okay, under this condition, and we can show that our main PDE just has one solution. So a more precise statement is the following. So assume f has a lower bound, and the gz goes to infinity, when z goes to infinity, and then we can find the origin symmetric convex body such that its boundary M satisfy this PDE. So this is our main. So this is our main theorem. A couple of remarks. The first remark, by the duality. So if M satisfy our main equation, then its polar dual M star also satisfy a similar equation. So basically, you just switch the role of f and g. So by the same reason, so we can also assume g is bounded from below, and f goes to infinity when z goes to infinity. Okay. So why we assume the condition star, just because we want to obtain information of omega from the function of j. That means we want to determine the volume and the shape of omega. from the value of its function. So as I mentioned, the proof is based on Gauss curvature flow and the Minkowski ideas and the topological argument. So we will use the following. Gauss curvature flow, and so this flow is a gradient flow to the functional J. That means if MT is a solution to this gradient flow, and then the functional J will be non-decreasing, and the equality holds if and only if MT satisfies our main equation. Okay, probably I'll skip the sketch of proof. I'll just talk about the proof directly. Okay, the first step, we will choose an initial class of ellipses, and then this is our initial set, and then we will just run the flow with the initial surfaces in this set, and here we take a special action, and the key property is that we can prove the existence of good shape solutions at any time t. And the third step is the key step. And once we have this key step, and we can easily find a nice object n star, and such that the flow starting from n star will converge to a solution to our main equation. Okay, so the first one, let me introduce what is our eccentricity of ellipsoid. So for any ellipsoid with axis R1, R2 to Rn plus 1, we just define the eccentricity of this ellipsoid to be Rn plus 1 over R1. So by this definition, the eccentricity is always greater than or equal to 1, and in particular, the unit disk has the eccentricity 1. By Gauss lemma when we studied the Monge-Ampere equation, the Gauss lemma tells us for any convex body omega, and we can always find a unique ellipsoid E of omega with a maximum volume containing omega, such that E of omega is containing omega, and also omega is containing a rescaling of this ellipsoid E of omega. So this E of omega is called the maximal ellipsoid of omega. So roughly speaking, just says that we can approximate omega by an ellipsoid. So we define the eccentricity of a convex body to be the eccentricity of its maximal ellipsoid. So if the eccentricity is small, so this means that omega is of good shape. So as we mentioned, when we assume the condition star, so f, g, and even f is bounded from below and g goes to infinity when v goes to infinity, and under this condition, so we can relate the value of functional with the shape and the volume of our convex body. So the first lemma says that if the functional is small, and then the eccentricity is also small. So if J of omega is less than A, and then the eccentricity is also bounded by some constant. So that means the shape is not bad. The second one is, okay, if volume is too big, here V is a large constant. If volume is too big or too small, and then the functional will be large. In other words, if functional is small, and then the volume of the convex body is bounded from below and above. So by these two lemma, and we can fix three large constants, C0 and V0 and E bar. So C0 is about the functional, and V0 is about the volume, and E bar is about the eccentricity. And such that if either the eccentricity is greater than or equal to E bar, or the volume is large, or volume is small, and then the functional will be large. Okay, so then we define our initial set, which is just the initial data, and this just a special class of ellipses EI. So here we choose EI to be the set of all ellipses n, and centered at the origin, such that its eccentricity is bounded by E bar, and also volume is between two constant, 1 over pi over 4 0 and V0 times pi. So this is our initial set. I'll skip this construction. So actually you can show that show that this initial set EI is homomorphic to the 3 ball D3 in this is just a 3 ball in R3. So here we use the Hausdorff distance. So EI is homomorphic to the 3 ball. So next we will just run this random flow for any surface or any ellipse in our initial set EI. The problem is, okay, if you run any ellipse with our gradient flow, and then there is no control, then we don't have like a priori estimate. That means the flow may develop singularities, so we have no control. So in order to find a solution, we need to take some special action. So instead of just flowing any hypersurface, and here we will take a special action and define a modified flow. So we define the modified flow as follows. So for any convex body n, so we use mn bar t to denote our modified flow. So if the initial functional is less than C0, and then then we will just flow this n by our gradient flow. And we know that the functional is non-decreasing along the flow. So once the functional reaches C0 at some time t prime, and then we take action and we will stop the flow and freeze the solution. And we define for all time t greater than or equal to t prime, and then it is just given by mn t prime. Then next one is if the initial function is greater than or equal to C0, then it is stationary. So this is our modified flow. Our modified flow is a continuous flow. It is not smooth because we take this special action. So one important thing is that our modified flow will not develop any singularities just because we have the bound on the functional. Okay, so the key step is that we flow any ellipse in our initial set, and then we can show the existence of a good shape solution at any time t. So that means for any time t, we can always find the initial ellipse in our initial set EI, such that the maximal ellipsoid of our modified flow starting from n is the maximal ellipsoid of mn bar t is a unit disk D2 centered at our origin. So that means it is of good shape. So this is our key property. So the idea of this key property is from the min-max argument. So you can just imagine our initial path is like EI, which is just a set collection of some ellipses, and then we deform this path by the gradient flow to get a new path PT. So basically, this lemma says that, okay, no matter how you deform this path, so just for any deformed path, and we can always find a point such that it's functional. The value of the functional is less than or equal to the value of the disk D2. So just like our initial one is this initial path is this black curve, and then we deform the path because the functional is non-decreasing. So then it becomes the blue one and the green one. But no matter how we deform, we can always find a point below the value of the disk. So this will help us to locate some min-max point, maybe at this point. So this is our key lemma. The proof is just a proof by contradiction. So if this argument is not true, and then we can construct a retraction from EI to its boundary EI, because EI is homomorphic to D3, then the boundary boundary of course just a boundary of D3. But then the fixed point theorem tells us, okay, no such retraction from D3 to its boundary. So this is just a fixed point theorem. So this argument is a topological argument. Okay, I'll have 1 minute. I'll skip the construction of this retraction. And once we have this key lemma, the remaining part is just you can take a limit and find some n star. So n star will the flow from n star will converge to a solution. So you can do the same thing for the higher dimensional. Okay, maybe the final remark is so you can so we have considered this functional when the ambient space is a sphere and the Euclidean space. So it's never natural. Or also the remaining case is to consider the case when the ambient space is a hyperbolic space. Okay, I'll just stop here. Thank you.
Thank you, Qiang. That was great.
Thanks.
Also give you a clap emoji. There we go. Got a few minutes for questions. Anyone have questions? No? My question was actually already, you just said it on your slide about the hyperbolic space.
Yeah,
so maybe you could give us a few words about how that goes. Is it significantly different?
Yeah, we are working on this, but we don't have like two big programs. So in this case, we can define a convex body in hyperbolic space. Then I do, and unlike the case in sphere and Euclidean space, means the polar dual or the dual body is some convex body in the de Sitter space. So that's the duality. And also, I think in the hyperbolic space, the convexity maybe is, the assumption convexity is just two-weak. So maybe you can consider,
there's a few different notions. Yeah.
Maybe you can consider the holoconvex,
right.
holoconvexity, and then to just to study the functional, because in the hyperbolic space, when we once we know the value of the functional, actually we don't have the information about the shape of the convex body or the volume of the convex body. So somehow we cannot. So it's not that easy to relate the value of the functional with information of the convex body. Yeah, we are working on this, but if if you are interested, you can just definitely work on this problem, because the functional is a quite basic functional. It's quite elegant. It's just some weighted sum of weighted volumes of weighted volumes.
It's interesting. Matt, did you want to say something?
Oh yeah, I was going to ask. Well, not if you're not finished with that thought, I guess. I was going to ask if
I'm finished as I need to be.
The centro-affine curvature, was that? It looked like it was scale invariant.
Yes. It just it's invariant under special linear group.
But not. I'm going to guess it's not conformally invariant though.
Yeah, no, it's not conformal. It's just defined by the Gauss, just Kp over U2 n plus 2.
It's not scale invariant, actually.
Oh, it's right. It's divided by, so it's not scale. Right.
Also in the like LP Minkowski problem, the centro-affine case is a critical case. So the solutions are the solutions to the centro-affine case is not known.
I guess the lack of scale invariance doesn't make a problem here. I mean, you can just constrain it. Yeah. Cool. Any more questions? a little chat saying thank you. So that's very nice. Okay, then I'll thank Qiang again.
Okay, thank you.
Wonderful
Yeah,
talk.
thank you. Let me stop sharing my screen.